Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah. And good morning everyone. My name is Seta Samsiana. This is my team. Setya Supratno, Subhan Awaludin Muhammad, Sugeng, Taufikur Rahman, and Amin Bakri. Okay, we are from Unisma Bekasi. Today I'd like to talk about our project, implementation of the Lagrange interpolation function in the motion planning system of a 1DOF robot arm. And now I plan to speak about 10 minutes, and I'd still be like to answer any question at the end of my presentation, and so please hold your question if you have any. Thank you. Okay, we talk about robot. Robot is the one of the mean that can help human tasks or work, and the movement of the robot manipulator is carried out by the arm. Arm is a link and join. This is join, and this is link. Problem is how to make the robot motion trajectory using Lagrange interpolation. And our purpose is designing two robotic motion trajectory system on a 1DOF manipulator robot that uses Lagrange interpolation as a knowledge base in printing the shape of the trajectory. Now, the limitation of the problem in this final project are, we have 4. 1. Effector robot is the segment to pass through for stopping point for stopping, okay. And we have for trajectory of the robot that is built is the form a semicircle. This is semicircle, and we use Arduino Uno, and we use a rotary encoder as an angle sensor. This is interpolation Lagrange. Interpolation, in a mechanical sense, is an estimate of a middle value from a set of known value. And interpolation is used to estimate to function only with known data. Interpolation. This is 1, 2, 3, 4. Our degree of freedom. This is for the picture. Making robot arm always consists on arm link and join. So the more join the robot move, more complex will be. And robot arm usually consists of several joints including the face, shoulder, elbow, first feet, and first rod. We use kinematic in first 2 for in here, okay. Angle. Inverse kinematic converts point coordinate into angle value. Okay, our method is we using the system design method for our project. First time we study of literature and motion track design, and then motion track planner software code assembly, then testing the result of the motion trajectory, analysis of the result of the motion robot arm before result of the motion trajectory, and then result of the motion robot arm on trajectory. And the last, prepare of the report. We use Arduino Uno, we use motor servo, rotary recorder, and this is our set. System assembly result, input voltase, and then Arduino Uno, motor servo, rotary encoder. In Arduino again, if we use set point as well, motor servo again, and arm motion. This is a picture of cable connection, motor servo, and encoder. How it works? First, we input for coordinate. So, Interpolasi Lagrange will calculate. Then, inverse kinematic calculation. So, moving arm, they are moving, have motion, and then this is result test system for electrical test, power supply, output voltase. We use 3 tests, 1, 2nd, and the 3rd. This is test motion. Input point coordinate. And then Arduino Uno will Interpolasi Lagrange like that. And Interpolasi Lagrange in Excel like this. We have 4 data. And this is Lagrange Interpolasi reading result on Arduino Uno, serial number, like this picture. This is our graph of motion path test result. This is test, the first test. Input 4 coordinate, 1 coordinate. 1, 2, 3, 4, and we have 4 point coordinate to 125 point coordinate in first test. How about the second test? We input for coordinate, and from 4 point coordinate we have 79 point coordinate. We have 79 coordinate, and then the third test we have from 4 point coordinate to 129 point coordinate. This is before Interpolasi Lagrange, and then after Interpolasi Lagrange. So, robot testing again trajectory point like this. Okay. Yellow is sensor and red is motor servo motion. And then testing the robot motion again here. This is we use rise time, delay time, steady state time, and peak time. use for rise time. Okay, and here for rise time, and for delay time we have 12 seconds. For steady state we have 21 seconds. For peak time we have 21 seconds too. This is first testing for robot motion, and the second we have rise time 9 seconds. For delay seven, 30 seconds and 30 seconds too. I think steady time and peak time same time. This is the test. This is the test, and this is first test, second test, and third test. And here we can see point for rise time, delay, steady state time, and peak time. Okay, conclusion. In this project is, it has been successfully predicted the motion trajectory of the robotic arm using Lagrange interpolation. From the test result, the rise time, peak time, and steady state time for each experiment were different depending on the initial value of the stop point. And in the process of working, this initial stop point will affect the number of new stop points after the Lagrange interpolation process. For example, for the first, we tried the rise time in 15 seconds, delay time 20 seconds, and the steady state time on the peak time are 21 seconds. While the second experiment increased, 9 seconds of time, 7 seconds of delay, steady state time, and 30 seconds of peak time. Then, for the third experiment, the rise time is 70 seconds of delay time, 30 seconds steady state time, and peak time 22 seconds. Okay, by looking at the result, the overshoot value and the steady state error value is 0%, where the output value produced is accorded with the input value. And based on the graph, before, okay, the form of the transition response follow the value of the stopover point made in the form of overdamp response. Okay, this is our project, and thank you for coming. So if you any question, with pleasure I'm answer, and thank you. Assalamualaikum warahmatullahi wabarakatuh.